transport layer is fundamental to the proper functioning of the network architecture of every other layer. For example, the Internet layer cannot guarantee the delivery of information to its destination. It's the transport layer that will play this role. The two most common protocols in the transport layer are TCP, Transmission Control Protocol, and UDP, User Datagram Protocol. The main service the transport layer provides is monitoring communication between the applications of the source hosts and destination hosts. This is called session multiplexing, and both UDP and TCP do it. The biggest difference between the two protocols is that TCP guarantees the correct delivery of the data, while UDP does not. Session multiplexing, i.e. communications between multiple types of applications on the network at once, happens all the time. For example, just doing a web search while listening to streaming music might well involve multiplexing. Multiplexing allows an IP host to simultaneously support multiple sessions and manage streams on the same link. A session is created when a source machine has to send data to a destination machine. To transmit data applications, the transport layer needs to identify the target application. To identify and send data to specific applications, TCP/IP uses port numbers. Each process that uses the network gets a unique port number on the host. This number is used in the header of the transport layer to identify which application the data is associated with. For example, port 80 is reserved for HTTP, Hypertext Transfer Protocol, used for the web, and 53 for DNS, Domain Name System. TCP separates different-sized data blocks from the application layer and prepares them to be sent over the network. Each fragment is divided into smaller segments. The size of these segments is determined by the MTU, Maximum Transmission Unit. MTU is what allows you to define the maximum byte size of a packet before it's transmitted over the network. By default, the MTU of IP is 1500 bytes. Unlike TCP, UDP doesn't provide segmentation services. It prefers to leave this job to the applications. If a sender transmits packets faster than the receiver can process them, then the receiver will tell the sender to send them again. It's the TCP protocol that's responsible for detecting and retransmitting any packets that were left behind. The more broadcasts there are, the more latency there will be in the communication. Flow control helps avoid latency by speeding up each transmission, but also decreasing the number of transmissions. Flow control is based on returns generated by the receiver. After sending each packet, the sender waits for a response from the receiver before sending the next one. On the other hand, if the RTT, the round-trip time, sharp slowdown. The RTT is a parameter which sets a limit on how long a signal can take to travel the whole of a closed circuit. To improve network efficiency, a mechanism called windowing is combined with flow control. This allows the computer receiving the data to tell the sender how much it can receive. This prevents congestion in the network. In the transport layer, a connection-oriented protocol allows you to establish a session between two IP hosts and maintain it throughout the transmission. TCP provides reliable connection-oriented transport for application data. TCP is very reliable because it can detect and retransmit packets that have been abandoned. It may also know whether data is duplicated or lost. And it helps prevent congestion on the network. When we use the terms reliable and unreliable, we're talking about two different types of connections. TCP is a connection-oriented protocol that's designed to ensure reliable transport, a controlled flow, and guaranteed delivery of all the IP packets sent with it. That's why it's referred to as a reliable protocol. As for UDP, it's a seamless protocol that relies on applications to sequence packets as well as to detect if any are abandoned, and to decide what to do if they are. It's therefore considered unreliable. Some types of applications need a guarantee that packets will arrive safely and in the right order, because even one missing packet could kill the entire data chain. TCP uses 3 steps to establish a connection. The process is kind of like making a phone call. The phone rings and the person who picks up says, "Hello?" The caller says who they are and asks if the other person is who they're looking for. Then the caller says who they are and the conversation can start. Let's see how this compares to the 3-way handshake of TCP. First, PCA sends an SYN packet to PCB to ask it to set up a session. The sequence number is randomly generated. For our example, let's say it's 0. Then PCB responds to the SYN with a SYN ACK. The ACK, acknowledgement number, is equal to the sequence number of the previous packet, incremented by 1, so that's 1 here. But PCB will generate its own random number for the sequence number of the SYN ACK packet. Again, let's keep things simple and say it's 0. And finally, if PCA accepts the SYN ACK, it sends an ACK packet to establish the connection. The ACK number is equal to the sequence number of the previous packet, incremented by 1. Full duplex communication is now established between the two PCs. This multi-step exchange, with sequence and acknowledgement numbers, allows the protocol to know if data has been lost or duplicated. The main applications that use TCP are web browsers, email, FTP such as printers, and database transactions. Not every application needs reliability. For example, if 1 or 2 segments of a streaming video are lost, it just creates a small disturbance in the stream, a little jerk in the video that you might not even notice. The main applications that use UDP are DNS, streaming video, voice over IP, and TFTP, Trivial File Transfer Protocol, a much simpler version of FTP that's often used to boot or update the firmware on embedded devices. Unlike TCP, UDP doesn't need to connect with the receiver. It's known as a connectionless protocol.